Alright, so let's go through the try yourself 2 binary star question from Meridian JC. So the very first part is to define G field strength, right? Okay, simple. So this is the amount of G force acting per unit mass, right? Okay, for part B, we are given 2 stars of equal mass in a circular orbit orbiting a common center as shown as on figure 13.1, right? So there is because they are the same mass, meaning that the center of gravity of the system is exactly at the center. So means that these 2 stars are actually orbiting around this part. Okay, so with this, right, we are asked to show that the speed of each star, right, v in terms of g, m, and r. Okay, so of course this is a showing question, means that we need to provide some statement. So the first part which say that g force provide the centripetal force. So okay, so let's look at the system. So of course we know that 2 stars, right, they exert a G force on one another, and just take note that the 2 G force is Newton's third law, meaning that they have the same magnitude, same opposite direction. Okay, so how do I actually calculate the GM, the so-called G force, right? We need to use GMM over 2R bracket square. Because remember, right, the GMM over R, right, the distance, the R is actually the distance between the planet to the planet, right? So in this particular context, it's actually 2R. So that's why you don't put GMM over R square. If you put GMM over R square, it's wrong already. So the first case is where we learn, right, in this is the Earth, this is the satellite. So this satellite, right, I want to determine what is the G force, right? I simply just use GMM over R. It's the distance between the center of the Earth to the satellite. But for binary star, we need to know that, binary star, right? Okay, so this is the speed of the binary star. So the binary star actually is from here all the way to here. So that is the distance. So this is 2R. So GMM over 2R bracket square. So the G force, right, will provide the centripetal force, meaning mv squared over R. What is the R right here? The R right here is actually the radius of the circle. For example, right, we know that we are orbiting around this center right here. So the radius of the circle is from here all the way to here. So that is why I put R here. Okay, with such, right, with this I can actually manipulate. So for example, we put GMM, right? So GMM is just GM square over 4R square equal to MV square over R. The next part is I get rid of the R left and right hand side. So GM square over 4R. So I times R, I times R. So this will give you mv square, right? So you can see that mv square almost already. So I need to cancel the m. So you can see that right here. Then v is square root of gm over 4r. So the answer for first part will be square root of gm over 4r. So that is the part I answer. Okay, part 2, hence or otherwise show that the period of this star, right, is given as such. So since they say hence, right, so means that I must use the previous answer. So I must relate that the speed, right, the tangential speed right here. So v, there's a v right here, right? So this tangential speed is actually equal to r omega. And of course, omega is related to the period. Omega is equal to 2 pi over period. So I simply just need to manipulate. Okay, with this, I'll write down. So v is equal to this, right? Square root gm over 4r equal to r omega. Since I got square root, I need to square both sides so that the manipulation will be easier. So this is the second step. Gm over 4r equal to r square omega square. Okay. The third step, I move the r square right here to the left hand side. So I move, it will become gm over r cubed equal to omega square. So now I decided, I want to change the omega to 2 pi over t already. So 2 pi over t, you put inside. Of course, not to forget the square right here. So 2 pi over t holding bracket square will give you 4 pi square over t square. So, okay, almost already, right? You just need to do a bit of cross multiplication. So you cross t square with gm, you cross 4r cubed with 4 pi square. So this part, left hand side, this part will be right hand side. Then after that, gm throw over to the right hand side. Then you just need to square root. So t is equal to square root of 16 pi square r cubed over gm. In this case, you have shown that the period is given as such. Okay, now let's move on to part C. Okay, part C is a bit harder. So the total energy of this system is given as such, right? So E is equal to negative GMM over 4R. So there's a negative due to the fact that this thing, the system is bounded. Okay, we are asked to use the COE, right, to show that the total energy is given as such. Okay, so total energy is equal to GPE plus K1 plus K2. You might be wondering, right, how come got a K2? Because in the normal circumstances that we learned last week, right, is that, okay, the energy of Earth and satellite. So there's a satellite orbiting around the Earth, right? So you can see that the Earth is actually not moving. The thing that's moving actually is the satellite. Means that we only need to consider the kinetic energy of the satellite. So it's just, for this particular case, it's just total energy of satellite is, or the system, right, is GPE plus KE. Okay, but for binary system it's a bit different, because you look at the binary system, right, you notice that there are two stars and these two stars are moving. Means that this is your KE1, this is your KE2. So you must add both the kinetic energy of both stars together. Of course, not to forget our GPE lah. Okay, GPE, let's write down the total energy first. So the total energy of GPE, of the system is GPE is equal to negative GMM over 2R. So likewise, right, why is it 2R instead of R? Okay, for the first case, we know that satellite, I want to determine the GPE of the satellite, right, from the orbit to the center of Earth, right? This is your R. It's from the center of the Earth to the satellite. So that's why I put negative GMM over R. But for binary system, it's different. So the distance between these two binary stars is 2R. Means that I must put the total GP, right, is GMM over 2R. Always remember, this denominator, right, is always the distance between one thing to the next thing. Okay, so after that, I simply just write down K1. Okay, what is K1? K1 is equal to half mv square. Half m, so v square, right, we know that our what is it called, the speed, right, is gm square gm over 4r. So I simply just put gm over 4r. This is square already lah. So this will be gmm over 8r. This is only for one, so just right now gmm over 8r. Likewise, K2 is also gmm over 8r. So when you do the calculation, you should be able to get negative gmm over 4r. So that will be the total energy to calculate the total energy of the binary star system. Alright, so for part 2, explain how the loss of energy, right, implies that the orbital period will decrease. So this one also quite simple, because if you look at the equation, energy equal to negative gm square over 4r. If I say that the total energy decrease, right, it means that due to the fact that there's a negative here, so the radius of the thing must also decrease. Just explain in the direction can already. Okay, the last part will be for unstable star system, right, with radius given as such and mass given as such, right, the rate of decrease of the period is about 7.7 times 10 to the negative 5 seconds per year. So estimate in years, right, when will the stars crash into each other, meaning that the period must go all the way to 0. Okay, first thing, to calculate this, right, I need to use this thing right here. So t, right, equal to square root. So I want to determine what is the period initially. So period is equal to square root of 16 pi square, let me go back here, r cubed gm. So this will give you square root of 16 pi square. Remember to put in terms of the SI unit, 8 cube divide by g, right? Okay, g is 6.67 times 10 negative 11 multiply by big M, 3 times 10 30. So this will actually give you, let's calculate, so 16 pi square times 6.5 times 10 to the power of 8 to the power of 3. Okay, so divide by 6.67, 10 to the power negative 11, divide by 3 times 10 to the power of 30 bracket. Okay, so my whatever that's inside the square root is about 216726845.3. So I just need to square root. So square root is 216726845.3. Okay, so my period of the binary star is about 14721.64547 second. So this is the initial period. So of course, estimate the time right where the stars will crash into each other. I just need to know when will the period be equal to 0, because they say I decrease every year, right? 7 times 10 negative 5, so I simply just divide. So for example, 14721.64547 divide by about 7 times 10 negative 5. So this will give you, let's see, so about roughly 210,309,221 years. It's about 2.1 times 10 to the power of 1, 2, 3, 4, 5, 6, 7, 8 years. Or 2.1 times 10 to the power of 8 years. The so-called binary stars will actually crash into each other. So that is how we attempt this question.